Hey, what's up guys? My name is Ben Love. This is my video submission for the Junior Breakthrough Challenge. Currently I'm 18 years old and today I'm going to talk to you guys about fractals. Before I start out, I want to highlight a specific understanding of geometry that I grew up with. This is known as the Euclidean geometry, named after the Greek mathematician Euclid in his math textbook that he wrote. And this is pretty much the geometry of what we might consider sort of perfect shapes. You know, you got perfect circles, your perfect right triangles, rectangles, and all those sorts of shapes. And these are the kinds of shapes that we grew up with on our tests and on the SAT and the ACT and all those sorts of things. And while those things are very useful for understanding really core math principles, for example, proofs in geometry, you know, those are essential in how we can, you know, angle, side, angle, and all those things. But when I look at the real world outside, or when I look at a tree, it doesn't look as perfect. And this has sort of bothered me from a very young age on how, you know, it seems like the formulas that I'm using in class are so precise and so accurate, and so it's seemingly just, they apply to perfect things and not necessarily to the real world, which looks to me somewhat chaotic. This is where fractals come in. Now, you may be wondering what a fractal is. A fractal is a shape, is a geometric shape that if you zoom in on the shape, or it's a geometric pattern, or you zoom out, it looks the same. So I have a little demonstration here for you guys. This is going to be my fractal example. This is known as the Von Koch snowflake. So I'm going to start out with a straight line here for my first shape. It's just going to be a straight line. And now I'm going to perform a process on the straight line where I take the middle third and I'm going to turn it into sort of a triangle, as seen in the next one. Now, repeating a process like this is known as iteration, and iteration is simply the repetition of a process. So, that is my first iteration of a process. I have my triangle here. All right, let's go to the second iteration. We got a straight line here, so I make a triangle in the middle, as seen here. Got a straight line here, got a triangle here. Another straight line, make another triangle, and so forth for the last line. Now, as you can see, it repeats into this one, which also repeats into this one, and eventually you get infinitely tiny little triangles protruding from other triangles. And if you sort of completed this all the way around, you would see a snowflake-looking figure, and that's one of the best examples of a fractal, a snowflake. Benoit Mandelbrot once said, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." Benoit Mandelbrot is considered one of the great founders of fractal geometry. In fact, just a little background on him, he grew up in Poland, and after escaping Nazi Germany, he came to America in the 20th century, mid-20th century, and he started working for IBM. And he had always had these ideas of fractals in his head when he saw the chaos of nature, but he was never able to do much research because, like we saw in our snowflake example, you can't really get too far into these sort of things by hand. You really need a computer processor to do all these, you know, hundreds and thousands of iterations. You know, that would be just impossible to actually develop good research by hand. And so he was able to do this. And that's really how a lot of our research on fractals comes from today, computers. I have a quote here from Google, or at least what Google says about fractals. "Fractals are useful in modeling structures, such as eroded coastlines or snowflakes. For example, measuring the coast of Britain. If you picture zooming in or zooming out, you know, all the intricacies and snowflakes like we heard, in which similar patterns recur at progressively smaller scales, and in describing partly random or chaotic phenomena such as crystal growth, fluid turbulence, and galaxy formation." Galaxy formation. That's pretty crazy when you think about it, how fractals, we can see fractal patterns in almost every area of natural sciences. Story time. There was once a ham radio operator by the name of Nathan Cohen. And in the middle of the 20th century, he attended a conference in Hungary where Dr. Mandelbrot was giving a talk on the large-scale structure of the universe in relation to fractals. After this conference, Cohen really took this idea of self-similarity and repetition, iteration, down to what he knew, which was, antennas and radios. And so what he did is he had an antenna, and so he bent it, and he bent it again and again into a fractal pattern iteration. And what he discovered was that it actually worked even better than before. This essentially was a scientific breakthrough in radio technology of fractal patterns. And now industrialization and the computer and all these new advancements have allowed us to make these small fractal-like radio chips that you can find in your phone, and they can pick up higher frequencies than the ones before. And really, that's one of the best examples of how fractal technology has helped shape our world. You can take your phone apart and look at it. I don't recommend it though, because you might hurt your phone. I'm going to wrap up with a couple more examples of how we can see fractals in everyday nature. From biology, you can see the fractal patterns in how the veins in our lungs branch out. That's really cool. Our kidneys, blood vessels in general. In nature, you can see fractals. In the clouds and the self-similarities, you can zoom in and out and still retain the same sort of cloud-like structure. Iterations you can see in mountains. You can actually look up moving like images of mountains of where you take just a bunch of simple triangles and then, okay, I want to divide this triangle up randomly into 3 parts and then that again. And you can take those iterations and you can actually see fully developed mountain landscapes, which is very exciting. Also rushing water. If you think of how chaotic that might seem in your head, it actually has a lot to do with fractals and how the water behaves. Couple favorites to end with. First is acoustic diffusers, which are little diffusers, and as the sound waves bounce off of them, how the sound waves bounce back is actually in a fractal pattern. And I'll add a link in the description to a video of this so you guys can see that. And of course, my favorite, Star Wars Episode 3, when Anakin and Obi-Wan are dueling, on Mustafar, and they're on the crane, and the lava's coming up, and it's splashing around. They used fractal technology in digital arts, in graphing, to make it look realistic, like actual lava. So my point is, you don't have Star Wars without fractals, and that's pretty cool. I did want to point out one thing that I stumbled across last week actually is a little essay by Laurent Nathanael in 2009, and he's attempting to use fractals in scale relativity theory to unify quantum physics and relativity theory. Now that's a mouthful, but it's crazy how, like Mandelbrot was even talking about earlier, how fractals really does pertain to the large structure of the universe and even relativity. But again, I do want to repeat, there's a lot of value in Euclidean geometry, in the straight shapes that we talked about earlier. That's how we build skyscrapers. That's how all of our infrastructure is built on, square shapes, because if you don't have a sturdy skyscraper, no one's going to want to work in it. So, in conclusion, fractal geometry is the way that we mathematically represent the clouds and the flowers that we see in nature, and also how we understand the principles and the processes that guided them and created what we observe today. Therefore, I implore all aspiring mathematicians, engineers, scientists, and the like to practice thinking in fractals, because it has increasingly been proven to be very relatable to how we observe and test and come up with conclusions and theories about the natural world. So thanks for watching, and I hope you learned something about fractals.